All right, so this brings us to the very last thing we need to review, which is harmonic oscillators and periodic motion. I saved this for last because we did it most recently. And also, I want to be fresh in your mind because looking back over the last 5 years of AP exams, I think this is one of the questions that is more likely than not to show up. So let's just quickly review what we know. First of all, when you have an ideal spring, so an ideal spring is one that has no mass itself, it follows what's called Hooke's law, which is that the force that it exerts is always equal to K times the distance it is displaced. And I'm going to use delta x to remind us that it's how much it's displaced. Now, on your reference sheet, there's an absolute value here. What I'm going to do is just put a negative here with a sub s there. Just remember that the force that the spring exerts is always opposite the distance it's stretched. So if we stretch it from x0 over here to x, so we pull this thing out, so now it's over here, let's say, and this is x, we don't use x, we use x minus x0. It's the distance that's been stretched from equilibrium. That's what this thing is here, delta x. So an ideal spring follows this law. That means that if you were to make a plot of the absolute value of the force based on the distance it is stretched, you would get a straight line whose slope is k. All right? So if you had to design an experiment where you're trying to find the spring constant, you could plot the force it takes to stretch it, the distance it is stretched by that force, plot those, and the slope will tell you the spring constant k. When we're trying to find the energy, remember the work that is done is the force times the distance that force acts. So that looks something like this. And if they're not in the same direction, there was a cosine in between them. For a spring, the force is all A times delta x, and the distance you stretch it is delta x. So you get a squared. The force, so basically what we're doing is we're finding the area under the curve here. And so it's a triangle. If you were trying to find the area under a curve like this, the force, the maximum force you'd exert would be k times delta x. So this is k times delta x. This is delta x, and it's 1/2 of that. So this is the energy stored in the spring. It's how much work it takes to store a spring. And the important thing there is that if you were to graph the energy stored in the spring versus delta x, it is proportional to delta x squared. It would increase like this. So doubling the distance the spring is stretched would quadruple the force that is exerted, it would quadruple the energy that is stored in the spring. Okay, so that was the first thing, which is ideal springs. And I will give you guys a copy of this because you're allowed, this is an open note test, so you can use it too. You don't have to take your own notes. The second thing we looked at were harmonic oscillators. And so the idea was that if you had a mass m attached to a spring whose spring constant was k, and you disturb this from equilibrium, it would oscillate back and forth. And so its position, x, as a function of time, could be written as the amplitude times the cosine of omega t plus however far it was from the reference point at the beginning at equilibrium. So we call this the equilibrium position. We call A the amplitude. So remember, amplitude is how much it's stretched from equilibrium. So if it starts here and we stretch it 10 centimeters to the right and let it go, it'll go to right, left, right, left, right, left. And so this is the amplitude. T is the time that's gone by, and omega is the angular frequency. That was the angular velocity of the wheel that was spinning. More importantly, it is equal to 2 pi divided by the period of the oscillation. And you can use those relationships to solve problems. When a harmonic oscillator is at its maximum displacement, all of its energy is in the spring. So the total energy of a harmonic oscillator is 1/2 k times a squared. That's the total energy. And if it's not all the way at its extreme point, then the energy is somehow mixed up between kinetic and potential. And so the kinetic energy will always be 1/2 mv squared, and the potential energy will be 1/2 k times delta x squared, where delta x is however far it's stretched at that instant. So this is the equation that tells us the relationship between the energy in a harmonic oscillator. Okay? If you want to know the maximum velocity will be when all of the energy, 1/2 k squared, is kinetic. And that's when it's at the equilibrium position. So as it passes through its equilibrium position, no energy is stored in the spring. It's all kinetic. So to find the maximum velocity, so if you're asked to find V max, that is going to be when delta x equals 0. So make delta x equal 0 and solve this equation. All right. Some other things to remember. If this thing is oscillating back and forth, and when it reaches its very, very farthest point, it's not moving. If you were to drop another weight on there, then you wouldn't change the energy of the system. It would have the same amount of energy. Okay? On the other hand, if you dropped a weight at the middle when it's passing equilibrium, now it's in motion, and now adding that weight will actually slow it down. So the thing to remember is that if you have a system, and let's say this is equilibrium, so here's my mass, and this is equilibrium, but when it's way out here at its amplitude, the farthest point from equilibrium, if you drop another weight on top here so they stick, then energy is conserved because it wasn't moving, so no kinetic energy is lost if you drop something onto something that's not moving. All right, because all the energy was stored in the spring and that won't change. However, if you drop it on as it's passing equilibrium, now it's moving, and dropping another weight on there causes it to slow down, and momentum will be conserved. So if you're asking yourself, hey, is this a problem involving momentum or energy conservation? Just think about what's conserved. If it's not moving out at the end, then energy will be conserved. It'll still have the same amount of energy as it oscillates back and forth. All right. A quick reminder of some other things we did. The period of the period of a mass on a spring is 2 pi square root of m over k. You guys know that one. And if it's a pendulum, the period of a pendulum is 2 pi square root of L over G. And remember, the period of a pendulum does not depend on the mass. Making the mass bigger doesn't change the period of a pendulum. Okay? So this is all review. It's just my, sort of last minute. This is something we haven't touched on in the last 3 weeks as we've been reviewing. I'm not going to assign a problem with this, but that's just a quick overview of harmonic oscillators and some of the important points. All right? And I'll attach a PDF of this so that you can use it as a reference because it's an open note test.